First, some announcements. Exam 1 has been graded and homework 2 has also been graded. So both of them are up on Gradescope. All you did very well on the exam. The max was 25. The median was 21.63, which is about 87% of the max grade. And mean is 20.87, which is about 84%. And as I said at the beginning, the grading scheme is roughly that anyone above 90 will definitely get an A. Anyone above B will get a B at least. Above 80 will get at least a B. And I might change the threshold a little bit if I think not many people are above the cutoff. But I don't think that's going to be the case with you students here. Any questions about this? About the grading scheme or the cutoffs or anything like that? Okay. And there are 7 students whose scans we have some trouble. So if you don't see your exam graded already, we are on it. We should be able to do it in a day or two. You need to check through all the 200 exams to find your exams again, but we'll do it soon. Okay. And you have about a week to submit regrade requests on Gradescope. And be gentle with the TAs. Don't go to them for everything so that they don't have to regrade everything. Okay. All right. So homework 3 is also up. So keep that in mind. Okay. So last class we were talking about the limitations of regular languages or finite automata, right? So we said, okay, as good as they are, as simple as they are, they cannot even compute some simple languages. And we saw concrete proofs of that. They are the pumping lemma, right? They could not compute majority, they could not compute palindromes, they could not check whether a string had an equal number of zeros and ones, right? And what we'll do today is we saw how to use the pumping lemma, but we never really talked about where it comes from, right? Why should every regular language satisfy this seemingly miraculous property, right? That if there's a sufficiently long string in the language that forces your language to have many other strings that can be constructed from your starting string in some specific way. Okay, so we'll see the proof of the pumping lemma, which is the right picture. The picture is the proof. Okay, and then we'll see how to go beyond finite automaton, and then we'll take a leap basically to modern computers. Okay. All right. So here's the pumping lemma again. So what does it say? If L is a regular language, then it must satisfy the following property. For every string in the language, which is more than some length p, which depends on the language. So you don't get to choose p, but there is some number p, so that any string in the language of length more than that can be broken up into 3 pieces which satisfy these 3 properties. Okay, and remember this order of quantifiers, that's very you cannot mess with it. You don't get to choose p when you're trying to use the pumping lemma to disprove that the language is regular. You don't get to choose p, someone gives you p, but then the only real choice you have is in picking the string x, right? And then you have to show that no matter how you split up the string x, again, you don't have the choice in picking A, B, C, you'll get a contradiction. Okay? And after the class last time, there were some very nice questions. Let me ask one of them. So why doesn't the pumping lemma rule out the following language? Let's say L, which is just this string 0, 1, 0. What does the pumping lemma say about this language? This is a regular language, right? There's a single string, so I can build an automaton which just accepts that string. So it is a regular language. How would you apply the pumping lemma here? What does it say to this statement? Why is it even true? Any guesses? What does the pumping lemma say in this language, for this language? Well, it's kind of a question which is a non-question, because for the pumping lemma, you get to choose the number p. right? So for instance, what if I say p equals 10? Okay, then the conclusion of the lemma trivially holds because there is no string in the language of length more than 10, right? So pumping lemma only applies to strings in the language whose length is at least this number p. If there are no strings of that length, then it's kind of vacuously true. Okay, yeah?
Pumping lemma doesn't help us prove that the language is regular, right?
Yeah, it doesn't really prove that the language is regular. In fact, there are languages which satisfy the conclusion of the pumping lemma but are not regular. Yeah, it's a very good question. Any other questions? All right. So PL holds. Okay. So where does the pumping lemma come from? Why do regular languages satisfy this property? Okay. The punchline for the pumping lemma is that whenever you have finite state machine, by definition, there are only a finite number of states that the machine goes through. You might have an infinite long sequence of states, but the total number of types of states that you see is finite. It's small. Okay, so that's what we're going to exploit. Suppose L is a regular language. Okay. So we have to show that any regular language satisfies this property. That there is some number p and blah blah blah. So let's pick a regular language. What does it mean for the language to be regular? There must be a finite state machine or a DFA which accepts strings in the language and rejects all the things which are not in the language. Yeah?
Wait, we're proving the pumping lemma, not the question, right?
Oh yeah, we're proving the pumping lemma. Yeah. Proof of PL. Okay. So suppose L is a regular language. Well, if it is regular, this implies that there is a DFA, it's a D that accepts / recognizes L. Okay, meaning for every string in the language, d of x equals 1 if and only if x is in the language. Okay, now what should the number p be? We get to choose the number p when we're trying to prove the pumping lemma, right? We have to say that for every language there is some number p. So how do I choose the number p? I'm going to say let p equal number of states in, yeah?
Why we can choose P here, but yesterday.
Oh, so we don't get to choose p when we're using pumping lemma to get a contradiction.
Okay.
Right? So here we're proving the pumping lemma. So we're saying that for every language there is some number p. Okay? Yeah. Yeah, it's confusing. Like, you flipped everything now. Back, we're trying to prove the pumping lemma as opposed to trying to get a contradiction when we're trying to use it to get a contradiction to it being regular. Okay? All right. So let p be the number of states in this DFA. Okay, that's our choice. Now, what does the pumping lemma say? For every string x in the language, there must be a way to split it up. Right? So remember, now we need to show for all x belonging to L and of length greater than or equal to p, there is a way to partition such that the three properties hold. Okay, So the pumping lemma says that for every x in this language of length more than p, there is a way to partition it so that the three properties hold. Okay. So let's take a string x of length more than p, right? So now x has let's say x0, x1, x2, so on. That's length n, where maybe n is greater than or equal to p. Okay, it could be p, it could be p squared, whatever. Yeah.
Are these defined as the individual bits or the
Individual bits. Individual bits, yeah. So individual bits. Okay. So before writing down the formal proof, which is just a few lines, I'm going to draw a picture. So let's imagine what happens when I run this string through the finite automaton, right? Because in the language, the DFA D should end up in an accepting state. Okay, that's the least we know, right? It has to end up in an accepting state. So let's see. I start in state 0. Okay, and I read this bit, maybe a transition to some other state. Let's say S1. I read this bit, a transition to some other state. Oops. S2, and so on and so forth. So I go through the sequence of states. I'm just walking through the set of states that the finite automaton goes through. And how many states do we have here? Including the start state. It's a sequence of states. I started from 0, maybe I jumped to 4, maybe I jumped to 17, 11, 15, whatever. At the end, I have some sequence of states. But how many states do I have? Well, every time I read a bit, I jump, right? Okay, so the number of states is n plus 1. Yeah?
Couldn't you go back to the state where you previously visited us? You could go from, like, let's say, S3 back to S2.
Yeah, for sure, right? Because the automata can dictate you to go back.
Okay, so the number, it's not number of the states, it's number of states.
Yeah. I'm just copying, noting down. Okay, in time step, think of each and reading a bit in each time step. In time step 0, I'm in state 0. I read a bit, and then I'm in state 10. I'm kind of creating a time log of my computation so far. Okay? Yeah?
That's like, there are only like key states with like the length of the traversal.
Right. Yeah. So the total P is the description in the DFA, but the length of the string could be much longer. Right? So the sequence of things that I visit could be longer. Right? Okay? So, yeah, I end up with this n plus 1 states. Now, this n plus 1 is strictly more than p. Right? So the number of things that I'm passing through is strictly more than p, but the number of types of states is exactly p. Right? So what does that mean? What can you tell me about the sequence of states then? So imagine you have a finite automaton which has only 3 states, and I run it to an input which is 1 million bits long. Okay? Then at the very least, what can you say about the sequence of states that you see? Yeah?
I
Yeah, there have to be some repeats, right? There has to be something that you revisited. You can't be visiting new things every time because there are not that many types of states. Okay, so then the fancy name for that is, yeah, yes, the pigeonhole principle. I have n plus 1 pigeons and only p holes for them to box them in and put cages on them. So some two will have to go to the same box, right? By the pigeonhole principle, we must have a repeat. Okay, that is Si equals Sj for some I not equal to j. Let me call this S0. Right? So you must revisit some state at least twice. It could be the starting state, it could be the last state, whatever we have. You must visit at least one state twice. Okay. So now let me draw a slightly different picture of this sequence, right? Because there's a repeat, maybe I can review something. So there's a difference between, this is the state diagram of the DFA. Okay, so maybe I read a bit, I go to 17 and so forth. Okay, so what is happening is, maybe I read the first bit, I go to 4, and then I go to state 3, then I go to state 17, and then I keep doing something, right? I keep visiting new states. Okay, but then at some point I have to revisit a node that I already visited. Okay, so suppose that maybe this is a node that I repeated, so there is a loop here. Okay, and then I have new stuff coming in. There can be multiple loops, I don't care, but all I'm saying is that there's at least one loop when you kind of look at what's happening in the state diagram. And since you accepted in the end, you end up in an accepting state. Okay? Does this make sense? Yeah?
Should our get rate have 2 hours matches or?
Yeah, it should have that. I'm just kind of looking at the transitions that we took on the input X.
So,
Okay.
so it is, we must have a route that go back to the previous nodes, even though like without noticing the critical principle.
Well, I mean, the length is more, right? So that's why there's a repeat. Does it make sense? So just because there are many more things that my path is much longer than the total number of types of states, I must revisit something. Okay, so that's what you're going to use, nothing more than that. Okay, and this is kind of only part of the diagram. I'm just kind of drawing what's happening in the finite automaton as it passes through the input X. Okay, so now my claim is that this diagram tells us how to split up X into pieces so that we can pump X. Okay, so what do I mean? So here we were reading X0, we jumped here, X1, we jumped here, X2, we jumped here, so on. right? So each of the transitions was like in some bit. I read 0 and jumped. I read 1 and jumped, and so on. Okay. My claim now is that from this diagram, this suggests a way to split up X so that I can pump X while still being in the language. So what should those pieces be? Yeah?
X0, X1, X2, and then you can have simply whatever bit you need to go from 17 to 18, 18, 19, 19 to be accepted, and then G will be everything.
Yeah, that's perfect. So the nice thing here is that we can think of this as 3 pieces, right? There is the okay, that's too ambitious. Okay, so let me call the portion of X leading to the first loop, this portion as A, this portion as B, and this portion as C, as suggested. Okay, so why is this a good idea to do? Well, a finite automaton only remembers where you are. It doesn't remember how you got there, right? So because it's a loop here in this 17, even if this part was cut off from the input, you would end up taking the same path, right? You would just go on the yellow portion and then take the orange portion if the green portion was missing. Nothing else would change. Cutting out this green loop would not change what happens on the yellow and orange portions. Okay? And similarly, if I go around the loop twice, I will also end up in the same place. Right? Nothing else would change. Okay? So what does this say about A times C? When I run the finite automaton on the input A and C with the B portion corresponding to the loop cutoff, where will I end up in? In an accepting state. So let's say this is state 20, leads to okay, that will also lead to the same exact end state. And the acceptance only depends on the end state, right? The same thing if I repeat the loop twice. It's like going around a racing track, right? Some people run around, I just sit there, in the end I'm in the same place as they are. Okay? And that's what this loop is doing. I can choose to go around it as many times as I want, but the end state is going to be the same. The same for A times B. If I go around the loop twice, it leads to accept state as well. Okay? So similarly, the same is true for BBB, and no matter how many times I repeat it. In fact, they all lead to the same end state, not just any accept state, but all lead to the same exact end state, which was an accept state to begin with. Okay, so that's essentially the proof of the pumping lemma. We found a way to split up X into these 3 pieces so that we have the pumping property. There's one caveat that we need to show the length of A and B put together is smaller than P, which might not be true right away from this picture. Okay, but we just have to change the argument a little bit. Okay. Any questions about this? Yeah.
So there are multiple groups instead of single group. We also
Yeah, we can do any one of those loops. In some sense, you know, it's advantageous for us to choose the first loop that you see to make to have some control on the total length of A and B. Yeah.
Why can't there be like why does the edges 18, 19, 19 have to be on the node that's got the loop on it? Couldn't they be like on like a different node like within the loop?
Yeah, they can definitely be overlaps here. This is like a simplistic picture. Like, you know, these nodes could be like, you know, this could be a much more jumbled diagram, right?
Why don't they start like inside the loop?
No, well, they're looking at the first time you come back to the node 17 and then calling everything after that as C.
But how do we know that of like 17 onwards that's like there's a path from 17 to an accepting state?
Because the string X led to an accepting state. Right, so remember the string was an accepting string. That's I should emphasize that as X belongs to L, we end up in accept. Okay. So yeah.
In case that you have A, B, C, or let's just say you have like one state, so it's just a loop. How would you separate that in that case?
Right, so A would be the empty string then, like epsilon, B would be the loop portion, and C could be whatever is left. If there's nothing left, that's what it is. Yeah. Yeah, in the lemma, there are only two constraints, right? So we need B to be not empty, that is important. And that will be true because we said that there is a loop where you at least take one step. Okay? And we kind of took care of this portion. This is somewhat obvious because any loop means it's non-trivial. But this portion requires a little bit of extra argument. Okay? All right, so let's see. Let's write down the proof formally. Okay? So formally, we define S0 is 0 and Si is the transition diagram. Okay, this is just what the sequence of states that your machine visits on the input X, right? And we say as n is greater than or equal to p, there exists some two indices that are the same within the first p plus 1 positions. Okay, this is saying, maybe the string X you provided is 1,000,000 bits long, right? And my number of states was 10. So that means there are many loops. In particular, there will be a loop just within the first 11 positions, right? You might have many loops later on, but let me try and find the first loop that I see, which is going to happen within the first p plus 1 positions. Yeah?
Doesn't it have to be n plus 1? Because if n is greater than equal to p, then you can have exactly one.
No. So p is the total number of types of states, right? So as soon as I see more than p, I should have a loop. There's no way around that.
Can n be equal?
Yeah, it could be equal to p. So just saying that, then there won't be any contradiction, right? So we're starting numbering from 0. Okay, I know that's So 0, and then you have 1, and then there's like n plus 1 things here. Okay? Yeah, this all this numbers everything from 0, just like programmers. Okay? Yeah? Yeah, maybe you're right. Because I did a subtraction, yeah, you're right. Yeah. It should be from 1 to n, yeah. Okay. So we had this sequence, this is the same sequence as before, I just wrote it down in an equation, and I'm emphasizing this equation just to say that we should have a loop between the first p positions. After I read the first p bits in the string, there should be a loop. Okay? So that's it, and then, so let si equals sj, and I not equals j, with both less than or equal to p. Okay, so between S0, S1, S2 up to SP, there should be some two which are the same, and that's what I'm identifying. Okay, and now we can define A as x0, x1, xi minus 1. Don't worry about the border cases, like, if I is 0, that means this is the empty string, okay, or the empty string if I equals 0. You should really always think of this picture. Once I see the loop, everything before the loop is x, is A, everything in the loop is B. Okay. Any questions? So that's it. Now we have one, just as we argued before, A to the, whenever I repeat B any number of times, that will also belong to the language for all k greater than or equal to 0. Now A times C was in the language, A B C, A B squared C, all of those would be in the language, because no matter how many times I go around the loop, my end state is not going to change. Okay? And we also have the length of B is greater than 0. The length of B is basically j minus I, and since I is not equal to j, that's at least 1. So when you took the loop, you might end up in a loop after a single bit. If this, like, 0 goes to itself, that's a loop, I'm fine with it. Okay? But it's non-empty, that's all we care about. And finally, length of AB is less than or equal to P. Right? Because J is less than or equal to P. Okay? Any questions? All right. So, I mean, it's a mouthful of words for the proof, but the real deal is just this picture. By the pigeonhole principle, we have a loop, and the loop is the part that's where we're going to pump again and again. All right. So that's the pumping lemma, and we already saw how to use the pumping lemma to prove that certain languages are non-regular. Okay. So let's do one more example of using the pumping lemma to prove a language is non-regular, and we'll then see how to go around this limitation of regular languages, right? You want a model of computation to be powerful enough to at least compute majority, right? Yeah. Yeah, exactly.
So, like, index is 0 to t is p plus 1.
This number of states is p plus 1, but the number of bits you would read would be p. Right? Yeah. Any other questions? Yeah?
I was a bit confused on why p ends at xj minus 1.
Right, so because it's just the way we are defining the transitions, right? Like SI looks at xi minus 1, right? So that's why when I say if I'm looking at Sj, then I must have just read xj minus 1.
Oh, I see.
Right, like, when I'm going to S1, that means I just read the bit x0. Yeah. Okay. All right. Let's do one example. Application of the pumping lemma. Okay. So this is a so okay. Suppose my language is x equals 1 to the p. Oh, I cannot use p. Okay. So it's 1 to the k where k is a square, meaning, basically the number of ones is a square of a natural number. So in some sense, it's basically 1, 1, 1, 1, 1, 1, 1, 1. It's 1 to the 9, 1 to the 4, 1 to the 16, 1 to the 25, and so on. Okay. I want to say that this language is not regular. Makes sense? I mean, it's kind of a weird language in that it has only ones in it, but the number of ones is changing. It's going from having a single one to 4 ones to, 9, 16, 25 ones, and so on. Why is this language not regular? We are applying the pumping lemma. We follow the usual template, which is suppose that L is a regular language. Okay. And then there is a number P. Right? So we suppose that L is a regular language to get a contradiction. And we suppose, we start by saying, okay, there is some number P such that the conclusion of the pumping lemma holds. Okay. And now I have to do two things. First, I have to come up with my choice of the string x, right? That's my power. What string x should I choose? What do you think? In the sessions, I need something in the language, which if I pump, something good doesn't happen. 1 to the next square after p. That might work, but let me make it a little easier. Okay, so let me just choose x to be the string 1 to the p squared. Okay, I'm going to choose the string x which has p squared once in it, right? And this is in the language, the number of ones is a perfect square. And that I have made my choice and I have to live with it. And someone else is going to come and try and break it. Meaning they'll try and come and say that here's a partition under which you can pump it, but I have to rule that out, right? So now suppose x equals a times b times c such that b can be pumped, right? Why does this lead to a contradiction? Any ideas? What should a and b be together? It should be all ones, right? You know, the whole string is only ones. So a and b should also only be ones. Okay? So then the length b is all ones and length of b is less than p. Okay, less than or equal to p. So by the third property of the pumping lemma, that the length of a and b put together is at most p, we know that whatever b is, maybe a is the empty string, maybe a has some number of bits, the number of bits in b is small, is at most p. Okay, so we will critically use this in this argument. So now I want to say that you get a contradiction. Why? Yeah, exactly, right? So we need to have a times b times c be in the language, okay, by the pumping lemma, right? But the number of ones in equals p squared plus length of p. Okay, so I only increased the number of ones a little bit. How many ever ones there were in b, that's what I increased it by. If b had a single bit, then I increased it by 1 bit. If b had 10 bits, I increased it by 10 bits. So if b had, you know, p bits, then I might have increased it by p bits. So the length is at most p squared plus p. Okay, but what is the next square after p squared? Right? So, but the next square after 1 to the p squared is p plus 1 whole squared, which is p squared plus 2p plus 1. Okay, so there are long gaps in the strings that are being accepted, and I only increase the length by p, and I'm not going to reach the next one. Okay, so this is a contradiction. All right. Okay, so this says that what's it a contradiction to? Contradiction to the language L being regular. Therefore, L is not a regular language. Okay, so the reason I'm doing this example is all the examples that somehow we did last time, we were looking at patterns, like, you know, there were zeros and ones, and that's what making things seemingly complicated. But this example illustrates that you don't really need like even 2 symbols to get non-regularity. Even just a sequence of ones could be hard to compute or recognize for a language depending on how many ones there are. Okay, and in the homework, one of the problems will ask you to kind of build on this thing and use this logic again. Okay. So there are tons of ways to apply the pumping lemma. If you look at Citrus textbook, there's some very nice problems where you have to be very creative in coming up with the right string x and then trying to find these ways to partition it. But for us, there are 2 conceptual things that we learned. First, there's a fundamental limitation to regular languages, right? And second, we have a concrete way to prove such limitations in many cases that we care about. Not exhaustively for all non-regular things, but it pretty much covers most of the things that we see in day-to-day life. Okay, so now let's take a break, and when we come back, we'll see how to go around this limitation. Yeah.
Okay.
Sure.
So the question I had was regarding the first question.
Hold on 1 second. So we started out, long ago, a century ago, we started out with Boolean circuits as a first model of computation. Realistic, powerful, but then they had a fundamental limitation that the input couldn't grow, right? And then we moved to models which can handle inputs of arbitrary length. And the simplest one we could find was DFA, right? But the DFAs themselves have a strong limitation. They cannot compute many things that we definitely want to compute. And any one of you might have seen that you can program your computers to do that computation, right? But our main goal for this course and in theory computation in general is to build a model which is going to be relevant even 100 years down the line, right? So what should that model be? It's definitely not DFAs, right? What should that model be? It's going to be Turing machines, okay? And as you see, it's a model that can handle growing input lengths and is as powerful as there can be. Okay. This is an amazing achievement. I mean, there really shouldn't have been such a clean answer, but there is for us. Okay. It's the equivalent of theory of everything in physics, right? We're looking for one theory which can explain everything. We couldn't find it, but in computing, we have one model which can capture everything, which is lucky for us. Okay, so let's build up to this model again in some seemingly simple extensions. Okay, the first thing, let's go back to DFAs, right? And as many of you already pointed out, so DFAs, when you're doing it, you have x0, you have the input, okay, and we read 1 bit at a time. So these were single pass constant memory algorithms, right? You make only 1 pass on the input and you have only a constant amount of memory. So how could you, if I asked you to augment it, what would you do to give additional power to DFAs? What would be some natural things you would try? How can I potentially extend DFAs to get more power out of it? Any suggestions? Yeah?
Allow for both growing memory and multiple processes.
All right. So allow, let's take each of these one at a time. Allow for multiple passes. Okay, so one way to think about it, allowing for multiple passes, is in a DFA, imagine there is like some symbol or like a head or an arrow which is pointing at the position that you're currently looking at, right? I see this position, I move this bit, and then I move to the right. And the head keeps moving like, one tape to the right every time. Okay, that's what a DFA is really, right? There's a long tape where the input is written. I read one bit and then I move one bit and then I move one bit and so on. Okay, what's one way to make this intuition of allowing multiple passes be multiple passes? Any suggestions? I want to say this makes it, if I'm only moving to the right, to the left every time, then I'm only making a single pass, right? Maybe if someone comes and says, oh, multiple passes means you can go to the end and then you can come back all the way and then you can keep going to the end and you can come back all the way. But that again seems a little silly and constrained, right? So what would be kind of a natural generalization which would go well beyond this constraint that you read each bit only once? Yeah? Yeah, so why limit your head, your counter, from only moving to the left, one direction? Okay, so let me rephrase this as, let me change it to allow moving back and forth or left/right on input. Okay, left and right, again, this is in our mind, right? We have this head, wherever this head is pointing, that's the bit we are reading, and that's kind of moving left and right. Earlier, it was only moving to the left, but now we can move both left and right. And the second limitation was the constant memory. Allow memory. That goes with input length. Okay, and what kind of memory do you want? There are two kinds of memory. What was that?
You want memory that's like operating memory, right?
Right, so you want something which you can both read as well as write. So that seems natural enough, right? Somehow you're saying not only is my memory, I can write once and then come back to it and re-edit my memory, can forget some things and make some new memories, right? We'd all like that, but at least Turing machines would like to give that power. Okay? So these two principles seem pretty natural extensions of DFAs, right? Yes, or they seem like leaps. These are not leaps, right? These are natural extensions, yeah?
So correlation or motivation on why we need to extend DFAs?
Right, so the reason we're trying to extend DFAs is that our goal is to build a model which can capture all efficiently computable things, right? And computing majority is definitely possible. That should be an easy function to compute. Checking for palindromes is an easy function to compute. But a model is not powerful enough to capture that, right? So it's not like, we found the model which will capture our modern computers and things to come, things that will build 10 years or 100 years down the line. So we need some work. So we're trying to get around and find a model which we think will capture everything that is possible to compute. Okay. It's not clear there should be an answer, right? There could be a hierarchy of things. Maybe for every model, there is something that you cannot compute, and then you have to add something, and then you have to add something, and so forth. We don't know, but let's at least try to extend this model. Okay? And allowing this head to move left and right and allowing memory, both of them seem very fairly natural. And essentially, that's all there is. Turing machines are equivalent. I say this with a big brain, with a huge, in a very informal way. And I think intuitively that's what they are. With DFS, which have left-right movement on input, and read-write memory. Okay. So this is what Turing machines will be. But let's define this formally. We'll just introduce some notation. It looks very close to DFA, so we don't have to it's not going to be too complicated, but we have to introduce some cumbersome notation at least for once. And as a historical anecdote, Turing defined Turing machines, which are extensions of DFAs, even before DFAs were defined. Right, so it's kind of funny that way. And yeah, all right. So what are the ingredients of the machine? So the machine will have access to a memory or a tape. Okay, and we should think of the memory or tape as unbounded length. Okay, it's infinitely long, although we won't access everything, but it can be as long as needed for the computation. We're not going to put any a priori bound on the memory, just as we weren't going to put any a priori bound on the input length that you're going to deal with. Okay? And we'll assume that the tape is loaded with the input. All right. So we kind of always try to minimize the number of pieces, right? So in this picture, we had the input tape where the head could move left and right, and then we also wanted to allow memory, okay? But there's no reason to have these two things separately. You can do that, nothing will change. But to keep the number of pieces smaller, we're just going to combine everything. There's this one long memory, and when you start out, what your memory has is the input and nothing else. This kind of your clean state. Imagine you're solving a problem, and before you start running, your hard drive just has the input and nothing else. And the bits following that are empty, and we will use a special symbol for empty. It changes from book to book, but I'll say it's this phi. Okay, that just means that that location is empty. Okay. And we also have states. So states are just like DFA, right? We said we're going to add head that can move left and right. We're going to add memory, but the notion of states should still stay. That was very useful. We were remembering at least something about the input, which dictated how we move when we read a bit, right? So states helps us make the computation local even if your memory is very long. right? So the memory can be very long, but my state is a fixed number, and what I do depends only on what I read. So you can imagine my head is starting somewhere here. I can move it left, I can move it right, and there's a state. Okay. Now, in each step of computation, you need a cell from memory where the head is, where the tape head is. Okay, so wherever your head is pointing, that's the bit that you read currently. Okay, and based on what you read and the state that you are in, you can perform some actions. Okay, so based on the state you're in, it's kind of your emotional state, different inputs can lead to different outcomes. Input bit read will perform action. Okay, and the actions are also simple. There are three kinds of actions. One, you first change state, write something where you are, and then move head. Okay, actually, let me write it this way. So it's a very local sort of operation. Okay, based on the state that I'm in and the bit that I read, I perform three steps. One, I change my own state, which is exactly like what a finite automaton would do. Right? When I see this bit, change your state to something else. That's like this arrow. So we change the state. But then the next two things are new. First, I'm allowed to write something on the head. It's not only read only. I can write something onto the head. So for instance, maybe I read this first bit and then I say, okay, replace it with 0. Write on the input. That part can also be overwritten. Anything in this memory cell can be overwritten if needed as dictated by these operations. Okay? And then I can move my head to the left or to the right. That's the intuitive picture of the entire Turing machine. Any questions? Okay. So move head. So either to left, we'll denote this as L. Either to right, we'll denote this as R, or either stay where you are, which means S. Okay, so you change state, you can write something at the head that you are in, and then either move the head to the left, to the right, or stay where we are. Yeah?
We do all three of these in one like transition, or
One transition. Every time we do something, we do all three of these. I mean, sometimes you might not be doing anything, right? You might not be writing something at all, but like you can think of it as writing the same thing again, right? That's just an easier way to kind of again minimize notation. Okay? All right. So the first question, well, this is, are they Turing machines? every DFA is automatically a Turing machine, right? You read the bit and you change the state. Do you write anything? Not really, right? So basically, you just write the same symbol. Writing the same thing again is equivalent to not writing anything. But what about the head? Right, you always move right. That's it. Okay. So yes. So what is the actions? Change state. Write same symbol. We don't change the input tape at all. And then move head to right. Okay. Yeah.
When we move ahead, do we always only go at most like 1 bit?
Yeah, at most 1 bit, yeah. That's important. So basically, even though we seem like we generalize the model of computational log, it's still local, right? In the sense that I'm not going to say you can jump from 1 millionth position to the start immediately. I can't say, okay, jump to starting position. You can maybe use that as a meta, like, routine, but the head will only move 1 step at a time. It's a very local view of computation, okay? Which is what makes it so powerful in the sense that, so realistic rather, right? Imagine you have this long tape. Every time this memory, you don't have to touch all of the cells in the memory. You just make local updates, but even the local updates, when you stitch them together, can do something amazing. Okay? All right, so let me define the Turing machine formally. So again, the formal definition kind of takes out half the beauty from the model. But as I said, we have to do it. So Turing machine has k states. Okay, this is the equivalent of states in the DFA. And for Turing machines, we definitely had to deal with binary alphabet for simplicity. I can also define Turing machines which only work on 0-1 strings, but it would make it quite cumbersome. So I'm going to increase the alphabet. There is sigma, which it denotes the alphabet that the Turing machine is going to process. So it could be 0, 1, or you could have some other symbols like 2, 3, 4, whatever you have. Okay. And the reason we do this is for some special properties. The alphabet will always contain 0, 1, a special symbol triangle, and a special symbol phi. Okay. So phi is like this empty cell, right? You had this long memory which was completely filled with empty cells at the beginning. Phi is supposed to signify that. And triangle is just for our convenience to mark the beginning of the tape. Okay, I'll talk about that in a second. So this must be a finite alphabet. And the description of the Turing machine is again going to be finite, which is very important. Even though it can deal with inputs which are unbounded length, the entire description of the machine is constant. Just like for DFA, you just have to specify the transition table, the number of states, transition table, then you're done. Similarly, for a Turing machine, you have to specify the transition function which determines the entire behavior of the Turing machine. And we'll denote the Turing machine transition function as delta. Okay. What does it take as input? What should it take as input? State. The state. So we'll again identify the states as the number 0, 1 through k minus 1, just as we did for DFAs. And what else should it take as input? the alphabet. Right? So what you do only depends on what state you are in and what bit you are standing on. What bit the head is on. Okay? I mean, you can really imagine a long tape and a single person who is following these instructions. I have k states, I move here, I look at the bit, then I do something in that. Okay? And what should the output be? So what should the transition function tell me? It has to tell me what I do. It has to tell me how to change my state. Right? What is the new state going to be? Okay, and it has to tell me what symbol I'm going to write at the current head position. Okay, that's so there are 3 actions to perform: change state, write something, move head. Okay, so K, sigma, and then L, R, S, and a special one called H. I'll tell you what H is in a second. Okay, so this is what to write at current head. Okay, and then this L means left, R means right, S means stay, and H means halt. Okay, meaning just stop running the machine now, you are done. Okay, terminate. That's what H means. Okay? So that's the description of the Turing machine. All right? Any questions? And how does the computation proceed? So you have the input tape. So the computation proceeds exactly with the following configuration at the beginning. Right? You start with the input loaded at the beginning of the tape, and we will assume that you have this triangle symbol at the very left to indicate that you reached the start of the tape. Okay, again, this is for convenience, and when we write things down, it's helpful to have a marking to say, okay, you're at the beginning of the tape. Because otherwise, I don't know if I reached the beginning or not from somewhere. Okay, and we start with head at x0. That's it. So now you start from here and state equals 0. This is your starting configuration. Your state is 0, your head is here, and then you start doing your computation. What does it mean to do the computation? You just keep following the transition function until you terminate or keep going forever. You just keep doing this, keep following the transition function. Okay? So repeat. So this is the state, and head equals 0. And one thing you can think of this tape as one long array, right? It's an infinite array, which we'll call T. Or maybe let me just say tape without any confusion. Okay? So the way the computation proceeds is you look at what the transition function asks you to do given the current state and the input bit that you read. Okay, head is like the index which tells you what bit you're reading. All right, I read this guy, now I move here, move there, whatever. Okay, and then I compute the new state. Maybe there is some the W that I have to write, and then I do an action. Based on this, update state to S prime. Then you take action. Okay, so take action means you change the contents of the tape as dictated by the action, and you change the head position as dictated by the action. Okay, as I said again, when you write it formally, it seems cumbersome, but intuitively what you're doing is moving the head based on the instruction and updating the tape as needed, and that's it. So if A equals L, then head should be so if the action said move the head to the left, I need to decrement whatever the head counter is, right? The indicator which marks where the head is. But I should not fall off the tape, so I say max of 0, head minus 1. Okay? And if A equals R, head is head plus 1. Okay? And if A equals A, then head equals head. Yeah?
Why don't we have to take the middle? So if it like exceeds the minus 1 spot.
Right, so the tape is infinite. You can definitely keep going to the right however long you want. Okay? And the only thing is you don't want it to become something silly, so you put this constraint that it's a one-sided infinite tape in some sense. Okay? And finally, if the action says halt, you just stop. Okay? Any questions? Yeah? Oh, then A equals L? So basically A equals L into
S prime W.
oh S prime. Oh right. Hold on. Yeah. So actually you're right. So that's true. So remember that the transition function has 3 things in its output: the new state that you might end up in, the new state that you might end up in, an alphabet that you will write, and then the action you will take. Okay, so the W is what you write in the location. Okay, so that's the symbol that I'm overwriting where I am. So I see I'm in this state, I read 0, it said, okay, write 1 now. So I write 1 and then say, okay, move my head to the left, to the right, to stay, or halt the computation. All right? Okay. And yeah, when we see an example, I think things will be clear. Intuitively, what you're saying is you have to specify this transition function, which tells you the local things you can do, and then things will follow naturally for the bigger picture. When you put these things together and follow the instructions, whatever happens will happen. Yeah?
the previous models, we defined an output.
Right.
There an output of
Yeah, we have to do that, definitely, right? So the output, there's a big difference in how we define the output here compared to the previous models. If the machine halts, okay, imagine you're writing a program, right? You end up with an infinite loop somehow in your program. There is no output, right? You only have an output when the program terminated. It's kind of the same thing here. If the machine halts, then the output is basically whatever is on the tape until the head position. Okay? Should be 0. Okay? So whatever is on the tape until the head position, you just write that as your output. Okay? And if the machine does not halt, then the output has the special perpendicular symbol, which is essentially saying that I failed to output any output. So that's like code dump essentially. Your program just gave up and you try to run your program and you ended up with a code dump. Okay? So this perpendicular symbol is not really an output, it just means that I didn't get anything. Okay? Yeah?
Is that first line tape 0 to tape, but that's output?
That's the output, yeah. This should be tape 1, sorry. Maybe let me write it. If machine halts, m of x equals this guy. Okay, and if machine does not halt, m of x is perpendicular. Okay. Yeah.
Can we halt them in like the middle of the thing?
Yeah, sure. But then the output would be from the start to wherever you halted. Okay, so naturally it can give multi-bit output in the model. Yeah?
If the head goes back to the start, like a triangle, the output is
The output would be the triangle. We have to fix some convention. So the triangle is also part of the tape, so you can overwrite it. Right? So I mean, again, different books follow different conventions. So in our textbook, we start with the convention that you have a triangle at the beginning. Okay? So just to help us know when you're like, there's something to mark the beginning. And we can overwrite it, or we can say the output does not include it. That both of them would be fine. Yeah?
So is triangle like tape 0 to begin with, or do we not really include triangle in the index of the tape?
Triangle is included in the index notation. The head is starting from x0 though. Oh, I should say head is at x0. Yeah.
Hello, everyone. So let's resume from where we were. Let's look at a specific example of a Turing machine just to kind of get a sense of the definitions. So the example I have in mind, the Turing machine has exactly one state, k equals 1. The alphabet is again the simplest possible. You have 0, 1, the binary alphabet, and then the two special symbols, the empty state, and then the start of the tape symbol. And the transitions are when I'm in state 0 and I'm in C the bit 0, I stay where I am, but I write 1 and move to the right. And there's only one state, so I'm always in state 0. When I see the bit 1, I stay in the same state, but I write 0 on top of where I am and then move to the right. And finally, when I'm in state 0 and I see the symbol 5, the empty state, The state doesn't change, what I'm writing doesn't change, but I halt. So what do you think this machine does? Well, it's not too hard to see that what this does is it flips the input. So it negates every coordinate of the input. And we can define for any Turing machine M a function which takes as input whatever a 0-1 string and gives as output an element presumably in the alphabet star union the perpendicular symbol. Sometimes it might not halt, so we have to consider that as well. And the convention will follow. There are many ways to define it, but the one that is used in the text and the one that's very useful is to define the output of the Turing machine as all the contents of the tape until and including the position of the head, right? If the machine halts. If it does not halt, then the output is just the perpendicular symbol, which is just to say that the machine hasn't halted. Okay, so that's the convention of the output, and let's see it in action now. There are many websites which allow us to simulate Turing machines. These are amazing tools. I coded up some of those things, and you're welcome to code up these by yourself. It's a lot of fun, I think. And one thing to keep in mind is, in some sense, Turing machines are even lower level than assembly level coding. Okay, in the sense that in assembly level coding, if you know what it is, you can do jumps, whereas in Turing machines, you cannot have random access, you cannot do jumps. It's very, very local steps, right? So you only see the bit that the head is at, and you can move the head only one position to the left or right. So it seems very limiting. It's very local computational model. But it can run forever, so maybe you can end up scanning the entire input. And just as a case in point, if we go back to this code that we have, flipping the bits, this is essentially like a DFA. We aren't using the power of the Turing machine, right? The head is only moving in one direction, to the right, and we're also not really using the memory too much. But that's fine. This is just as an example to see how Turing machines work. Okay, so here I'm going to load my machine, which I pre-coded. This is flip input. So the language in this simulator is a little bit different from what we are using, but the differences are very minor. The first one is that here you use the underscore as the equivalent of the empty symbol in our notation. And there's something called the accept state here, accept or reject states, which kind of perform the same functionality as halting in our notation. Right, so we simplified some things for notational purposes, but in coding, this particular simulator uses slightly different convention. And we'll look at the convention later on. Okay, so here's the input. Let me load it up. And remember always that the starting state of the starting configuration of the tape is that the input is loaded onto the tape, everything else is empty, and the head is on the first bit of the input. Okay, and here there is no triangle symbol to indicate the start of the tape, and that's a difference from this simulator, but let's not worry about that too much. Okay, and let me now run what happens when we start doing this. There's only one state, which we are calling Q0, and it reads that, it flips that, overwrites it, moves to the right. In our convention, we are thinking of moving the head to the right, but here in this animation, the tape is moving to the left, which is kind of the same, really. Okay, so the state is always the same. You reach the end and you stop. So this Q accept, as I said, is essentially like the halting state. Okay, and so this is just an illustration of the Turing machine. But just as a heads up, and kind of a preview of what we're going to do in the next lecture and so on, Turing machines are indeed quite powerful. As a first illustration of it, let's think of the language of palindromes, right? So remember, palindromes we showed were not a regular language. A string X is a palindrome, is in the palindrome's language if it's the same front and backwards. For instance, this input is exactly the same, right? So, maybe let me, so I coded up a Turing machine for palindromes, and we'll go through some parts of this code. It's a very long code, there's like 100 lines here. We won't do all of that in the next lecture, but we'll go over the main ingredients just to kind of illustrate how you can do many things just with these local steps, okay? And let's see, let me change the input and load it. So I loaded the input, and this string is not a palindrome. So the output of our machine should be 0, right? Because we want our function to output 0 when the string x is a palindrome and is not a palindrome, and 1 if it is a palindrome. So let me run it. Well, let me speed up the animation a little bit. It's taking too slow. Even more. Okay, this seems magical, but it came up with the right answer, 0. And essentially, as we'll see in the next lecture, the idea here is that even though you can only take local steps, what you can do is kind of read the first bit, remember what it is, go to the end, check if it's the same, then come back. Read the next bit, remember it, go to the end, check if it's the same, and so on. Okay, so let's actually give a string which is a palindrome to make it more interesting. Right. So here the output should be 1, and let's see what happens. So in some sense, it's remembered that the first bit was 1. That's the state go and 1. It checks the end. It found it. Now it goes to the start, reads the next bit. And it's kind of going again. Right? Let me speed it up. Even more. Okay, now it has to kind of clean up the tape because the output should be just 1, right? So voila. So we have the output, which is 1, and it made 64 steps. Okay. And if you want, you can kind of play with it a bit more. Let me say 1 here so that it is not a palindrome, but it kind of only sees it not too soon. I speeded it up a lot, and see the output is 0, which is as it should be. Okay, so we'll see how we are able to do it. And the intuition always is that even if the computation seems like it needs to read and remember things in the long range, you can do everything locally. And that's the real beauty and simplicity in Turing machines. Okay, so in the next class, we'll pick up from here. First, figure out how to write a Turing machine to recognize palindrome, and then maybe a couple of other examples. And then jump into studying their power, their properties, and things like that, just as we did for DFAs.